Welcome to E-Padasala program for PG students of computer science. So, I will be teaching you embedded systems for this course. Today, I will be giving you a lecture on introduction to computing. So, in this actually we will be looking at the definitions of the system, embedded systems, as well as the fundamentals of your computings and basic concepts of digital processing and logic circuits. And at the end we will be looking at how the system will be built up, so that the architecture also will be shown to you. So, basically the system we will be looking at, it is a way of working or organizing or performing one or more tasks according to a fixed set of rules or programs or plan, or I can call it as it is an arrangement in which all units will assemble and work together according to a program or a plan. So, this is actually a general definition, but we will be looking at in this course embedded system. So, in an embedded system it is different from your normal system. In what way? In the sense we will be having hardware as well as software. So, here an embedded system is a system which has a software embedded into a hardware, which makes a system which is dedicated for an application or a specific part of an application or a product or a part of larger system. So, it is a dedicated system, it can be made it into a part of a system, or it can be a many things combined together make a single system also. So, we will be using here this embedded system which will be made for a dedicated purpose. So, your software is embedded in the computer hardware, so that it will be used for only a particular specific purpose. So, this is the basic difference from your normal system and the embedded system, where before looking into your system development, first we need to know about the fundamentals for computers as well as what will be the digital systems we will be having. So, the first thing is, in the digital computing systems we will be looking at only bits, we will not be looking at numbers. So, when you are looking at bits we will be having zeros and ones. So, how we will be generating these binary values, that will be the first task. Then we will be knowing that how we will be working with your bits. So, usually in the real world we will be using only decimals, where the decimal numbers we will be calling it as 0 to 9, where we will be having a 10 different symbols. So, we will have a base of 10, but when you are looking at your binary number, we will be having we will be having the binary numbers which will have only zeros and 1. So, we have basically only 2 numbers, unique symbols as well as 2 numbers. So, it will have only a 2 base 2 as the system. So, when you are looking at this binary numbers, we will call always bits. Usually we will call your decimal numbers as only decimal system, where you will be 0 to 9 will be called it as digits, where these binary numbers will be called it as bits. So, how first we should know, when you wanted to process a particular number, we will be looking at only decimal numbers. So, when you are looking at decimal to binary, first we need to know, when you wanted to process a number, the number will be given in only decimal. So, if the decimal is given, I need to convert that decimal number into binary number. So, when I wanted to convert the decimal number into binary number, I have to follow a particular step. So, what I have to do is, I have to divide that particular number by 2 continuously and keep tracking of your reminders. So, when this process will be continuing and until you will be getting a 0. So, when the reminders are only considered and it will be written in the reverse order. This is the procedure to do your binary number conversion. We will just see that this is an example we have shown, where you just take it 25 is a binary number, decimal number. Now, I wanted to convert this into binary. So, what I have done over here is 25 by 2 is done. So, we will be getting 12 as your quotient as well as 1 as your reminder, where I will be keeping this 1 as a reminder, that will be of most important to me, and the 12 is again consecutively divided by 2. So, when I am dividing by 2, I will be getting a 0 and reminder as 0, 6 as a quotient and reminder as 0. So, now I will be taking 6 divided by 2. So, you will be getting a 3 and the remainder is 0. So, again I am dividing it by 2, I will get 1 as quotient and 1 as reminder. So, again 1 is divided by 2, where I will be getting quotient as 0 and remainder as 1. So, when I am getting a quotient as 0, this reminds me to stop this division by the time. So, now I will be looking at only the reminders. You just look at these reminders, where I will be in a position to take it from I will be in a position to write it from bottom to up. So, 1 1 0 0 1 1, this will be the equivalent number where I will be having it for my 25. So, 25 base 10 is equal to 1 1 0 0 1 base 2. This is the way we will be converting your decimal number into binary number. So, if we know how to convert decimal number into binary number, where we need to know how to convert a binary number into decimal also. So, for that we need to do a different procedure, where we will be looking at always, if I am having a decimal number, I will say that 10 power 0. So, it is 1, 10 power 1 is 10, tens place, and 10 power 2 hundreds place, maybe 10 power 3 it is thousands place. So, we will be looking at units place, tens place, hundreds place and thousands place. Same way here also, when I am looking at a binary number, I will say that the first position is 2 power 0. So, 1, the next position is 2 power 1, that means the weightage is 2 power 1, and this is 2 power 2. So, 4 is the weightage, 2 power 3 and 2 power 4. Based on that, these numbers will be having the weightage. So, now when I wanted to convert the whole number 1 1 0 0 1 1 into a decimal number. So, when I am converting it, I will be marking it 1 into 2 power 0, which is equal to 1, 0 into 2 power 1, which is equal to 0, 0 into 2 power 2, which is 4, which is also 0. So, 1 into 8 is 8. So, 1 into 2 power 4, which will be 16. So, now I am adding up this 16, 8, 0, 0 and 1. So, it comes to 25. Now, we will be knowing that how to convert 25 to a binary number, and we will be checking that, and we will be following a procedure which converts this 110012 to 25 decimal number. So, this is a way you will be converting your decimal number into binary as well as binary number into decimal. So, when you are looking at, as you know, if I am looking at 25, where I will be representing with the 5 bits. So, only we have 2 digits, this will be converted into 5 bits. So, if I am writing any other number, I should be in a position to represent it with more number of bits, that I wanted to minimize the number of bits. So, for that particular reason, we will going ahead with a different system. It is slightly related to your binary number system, where we will be using your hexadecimal system. So, the hexadecimal, what it means is, it will have 16 unique digits, that means 0 to 15 we will be taking it as 0 to 15, but we know that from 0 to 9 it is a unique number, but when I am looking at 10, 11 and other things, I need to give a different symbol. So, for that particular reason, I will convert this 10 into A, 11 into B, 12 into C and 13 into D, 14 into E and 15 into F. Now, all other numbers I will be having 0 to 9. Now, I will just say that if I am having, instead of having a 0 to 9 for a decimal system, 0 to 1 which will be of binary system, the hexadecimal system has 0 to 15, 16 numbers as the base numbers. So, what is the advantage over here is, each number where I will be having, up to 15, I can represent with only one number. So, now if I am, when I am looking at binary number, I can say 0 becomes 0 0 0 0. That means 4 bits I will be in a position to combine. How it becomes 4 bit is, 16 is equal to 2 power 4. So, to the base of 2 we will be having 4 bits if I am combining together, which makes 16. So, the 4 binary numbers are combined together to make a single hexadecimal number. So, it is very easy for me to represent any of the binary number into hexadecimal number by packing up 4 bits into a single hexadecimal value. So, now you just look at over there, I have 0 0 0 which will be 0. When I am looking at 1 1 1 0, then I will be calling this as E. When I am looking at 1 1 1 1, this will be converted into F. So, 15 is 1 1 1 1 in binary, this is converted into F over there. So, if I have 4 binary bits, that I will represent with a single hexadecimal number. This is the advantage over when you wanted to represent a number. If I am giving a hexadecimal number, when it is given to a digital system, this will be this converts this number into 4 bit number, and 4 bit is taken for the binary processing. So, now one of the system which makes writing up the binary numbers in a simple way is hexadecimal system. So, people always prefer to write binary numbers in hexadecimal system. So, you just see that this is an example where I have a binary number, I will be having something like 1 0 0 0 1, 1 1 1 1 1 1 0 1 0 1 in binary. When I wanted to represent in hex, I just make it from left to right, I am going in this direction. So, I will be grouping this 1010 as one number and 111 is one number and 1001 as another one number. So, now when I am making it 0101 is 1 plus 0 plus 4 is 5. So, I will call this number as 5 in hexadecimal, whereas here 11111 is nothing but a 15, where I will represent this 15 as f in my hexadecimal number. So, the same way here also 8 plus 0 plus 0 plus 1 is 9. So, the hexadecimal number is given as 9. So, now I can call this 9f5 is equivalent to this binary number. So, instead of writing 1000 11111110 I can write it 9f5 base 16. So, this way it is very simple for me to convert a binary number into hexadecimal, which and vice versa also possible. So, 5 can be written as expanded as a 4-bit number, that means 0101. So, that I can expand very easily also. So, now we have gone through all the number systems, binary binary as well as hexadecimal and all those number systems. Now, we wanted to know how to process these bits or binary numbers. For that we will be looking at, we will be going ahead with logic gates. So, these are the primary elements which helps us to process the binary numbers, which is nothing but your bits. This is the basic element for your digital computing. So, when I am looking at a logic gate, I will be having a AND gate, OR gate, inverter, NOT gate, NAND gate, NOR gate and XOR gate. So, these are the basic gates we will be having it. Based on that, we will be processing all your binary numbers, which is nothing but bits. So, first one is your AND gate. So, this AND gate which does x is equal to a dot b, which is nothing but I can call this dot as multiplication. So, a multiplied with b can be written as a dot b with x in binary operation. So, AND operation I can relate it to multiplication operation with your decimal number. So, this is the symbol with which I will be in a position to represent this AND gate, where it has 2 inputs and 1 output. So, if it is 2 input, in the sense I will be having 4 different combinations, where I have 0 0, 0 1, 1 0 and 1 1. So, if I am multiplying 0 multiplied with 0 is 0, 0 multiplied with 1 is 0, 1 multiplied with 0 is 0, 1 multiplied with 1 is 1. So, only I have I have given you this operation, dot operation is almost similar to multiplication. So, now I will go ahead with my OR gate a plus b. So, the symbol itself tells you that it is like addition. So, when I am adding it, this is the symbol with which the OR gate is represented. It takes 2 input and 1 output. So, 2 input as I said, 4 different combinations I can make it, will have a 0 0, 0 1, 1 0 and 1 1. So, now 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1 and 1 plus 1 is also equal to 1 over here, because I will be representing only one bit as an output. I will make it 1 plus 1 is equal to 1. But in binary addition, I can call 1 plus 1 when we are doing a real addition, by the time 1 plus 1 becomes 1 0. So, the next gate which will be of very important is inversion. Inversion is nothing but your NOT gate, where x is equal to a dash. I will call it as in a dash or a bar, both are similar. So, now this is the symbol with which this bubble tells you that it gets inverted. So, if I am inverting a inverted to x, I will call one input and one output. So, 0 and 1 is the only combination, 0 becomes 1 and 1 becomes 0. This is nothing but a inversion. So, which is nothing but a NOT gate. So, now when I am looking at XOR gate, this is actually a XORed with b, that means 2 input is there and it is XORed, will be getting 1 output. This is the symbol for XOR. So, it is complete, it is not like your addition or multiplication or your negative, inversion, all those things is not coming into picture. What it does is, if both are similar, then it gives you a result as 0, if both are different, then it gives you a result as 1. So, you just look at over here 0 0, because both are similar, the result is 0, 0 1, both the input are different, so the output is 1, 1 0, the inputs are different, so the output is 1, 1 1, both are similar, so it is 0. Rather, I can say that this is usually used for comparison purpose. If I am putting a bubble over there, you can imagine if I am putting this NOT gate followed by the XOR gate, after that if I am putting a NOT gate, I may get it, if both are similar, then I will get a 1. So, that way I will be in a position to do any process if I am having this AND gate, OR gate, NOT gate as well as XOR gate. So, I can make a combination of these gates to produce anything. For example, if I wanted to compare 2 bits, if both are similar, then only I will say that it will be 1. So, by the time I will make it XOR, for next is NOT gate, combined together will get XNOR, which will give you, if both are similar, it will give you the value as 1. So, that way I can make so many combinations like your NAND gate and NOR gate. So, your NAND gate is nothing but AND gate followed by a NOT. So, you just see that this is a symbol AND symbol along with the bubble which gives you a NAND gate. So, which is nothing but A dot B to the power to whole power dash, that means I am inverting the whole thing. Rather I can have 0 0 previously it will be multiplied. So, 0 0 is 0, now it gets inverted. So, this is 1. So, 0 into 1 multiplied I will be getting a 0, it is inverted 1. So, 0 1 0 is also 1. So, 1 1 in the AND gate it becomes 1, now it is inverted. So, it is 0. So, you just look at that this NAND gate is a inverted AND gate. So, the same way I have a NOR gate where A plus B the whole dash. So, A plus B is nothing but R, where I will be having 0 plus 0 is 0 inverted as 1, maybe 0 plus 0 is 0. So, inverted is 1, 0 plus 1 is 1. So, inverted is 0, 1 plus 0 is 1 which gets inverted as 0, 1 plus 1 is also 1 which gets inverted as 0. So, now you just see that this NOR gate gives you the result of 1 for only one combination which is 0 0. So, now these are the primary gates we will be having for processing your binary numbers. So, with the processing of all these things I should be in a position to implement any of the functions. So, any process you wanted to do it, that can be done with these gates combined together. So, if I am combining these gates I will make a digital circuit. That particular digital circuit is used for processing the digital digital values, which is nothing but binary numbers. So, I told this is a digital circuit. So, digital circuit is a combination of your gates, but it is made for a particular purpose. It will give you certain results. So, the first example is your adder, where your adder will have half adder as well as full adder. What is meant by half adder, what is meant by full adder is, if I am adding 2 bits, I will be in a position to get 2 results, one is sum and another one is carry. For example, if I have a value of 0 0, maybe I will be in a position to have, if it is 0 plus 0, I will be getting a 0, 1 plus 0 is equal to 1, whereas 0 plus 1 is equal to 1, if 1 plus 1 is equal to 1 0. This is what we wanted to have it. So, now you just see that this 0, 1, 1, 0, these are the units place values. So, I can say that I will get it in my sum, whereas if I am getting this as 1 0, where this 1 is a carry over here. So, when I am looking at the carry as well as sum. So, sum will be the results for all these values, whereas 1 plus 1 only will be giving you the carry. So, this is what we will be looking at when you are looking at adder. So, when I am looking at adder, you just see that your A and B are the inputs. If I am adding it through the XOR, I am doing it. XOR, what it does is 0 plus 0 is 0, 1 plus 0 is different. So, 1, 0 plus 1 is different. So, 1. So, remembering your XOR gate, it will give you, if 1 1 both are similar. So, 0. So, that will be given you the sum as the result, whereas when I am adding it 1 plus 1 which becomes 1 0. So, by the time this will be 0 and this will be 1. So, that is what happening when you are looking at your your half adder circuit. So, the same way this is for only adding up only 2 numbers. The same way if I am adding it for 3 numbers, what I have to do? So, by the time I will be going ahead with my full adder. So, when I am looking at full adder, I need to know how to do this. So, where I will be having A plus, B plus your carry, C is your carry. That means, if something I am getting it as a carry, that will be forwarded for next addition. So, for that particular reason we will be in a position to have all these full adder and all those things, we will be using it 3 bits added together. There also you just see that. So, when you are looking at A plus B, where I will be in a position to add these two numbers, I will be getting a result over here, and when I am looking at the third value also I wanted to add it, I am going for a full adder. So, when I am looking at a full adder, I will be looking at two half adders are combined together. So, A plus B plus C, which will be two XORs are added together, I will be getting a sum. Whereas, I am taking A B is added together to get a carry, and this again this carry which is also added together. I should get either these two are 1 or these two are 1 or these A and carry are 1. If any 2 is 1, I will be getting 1, I mean carry as 1. So, this is the basic concept. So, that particular concept is made it in a truth table. Through the truth table, I will be making, I will be simplifying the functions which I wanted to implement. For example, here sum and carry is my functions, I will reduce the equation. So, that particular equation is reduced through so many techniques using K-map or something else, or using certain formulas, I will be or rules, I will be minimizing or I will be making the equation should be optimized. Then I will be implementing that equations using this kind of logical gates. So, now I will be making this as a digital circuit. This digital circuit is made for a particular purpose, and I will be producing, these are the inputs, I will be in a position to get my outputs sum and carry. So, this is a best example for a digital circuit where we added two numbers, 2 bits as well as 3 bits. So, half adder and full adder will be used for adding binary bits. So, the next is one specific example is your decoder. So, what it does is, for example, if I have 4 persons, I wanted to address them. If 4 persons are there, I need a minimum of 2 bits to address them. So, if for example, I will have 4 persons, I will call it as Q 0, Q 1, Q 2 and Q 3. Now, I wanted to address them. I can address them by with 2 numbers 0 0 or 0 1 or 1 0 or 1 1. So, this is the way I will be in a position to address it. So, to generate 0 0 and 0 1, I am making use of A and it is inverted value 0, B and it is inverted value B. So, A, B are the 2 inputs. With that, I will be in a position to make A, B, A bar, B bar as 4 different combinations. Now, I am making it A bar, B bar, which will be my Q 0. Maybe if I am giving A bar B, then it will be my Q 1. So, that way A, B. So, now I will be in a position to select any one person by giving any one of the value with these A and B inputs. So, with the 2 values I can make 2 power 2 as 4 combinations. The same way if I have 8 persons, I can have 3 values. So, 2 power 3 is 8. So, 8 different combinations and I can make it and I can call them. So, these decoders are widely used for addressing a memory or addressing decoding in a computer design. That means, if I have a memory, I wanted to address each and every location. That can be done through this kind of, the address will be given over there, it gets decoded through this and it will be given in an elaborated way which uniquely identifies one place. So, this is a best example for a digital circuit where we will be using it for addressing memories. And the next important thing is your memory. So, the memory is also made up of only your digital digital circuits. See here, this is a fill flap where this is, I can call it as a NOR latch. This particular latch is used for storing a particular value. So, here the D latch is given over here, the whole D latch is given this way, and this has been the input is given over here, which whatever be the input I am giving it, which I will be storing it, I will be getting it as Q. If the whole thing is a fill flap where I should give either 0 or if I am giving a 1 over here, I should give a 0 over there. If I am giving a 0 over there, 1 it should be given over there. So, that only it has been given as D is directed directly and it is inverted and directed directly, and this is nothing but a clock. So, unless otherwise the clock is not present, I cannot access this. So, that is what I wanted to have a control over there. So, D is the number I wanted to, D is the value I wanted to store it over here. You just see that if I am giving a D is 0, already it has a value of Q, whatever be the value over here, I will not be bothered about that particular value. Now, if I am giving a D as a value of 0, the 0 will be there. If I am giving a value of 1, it will have value of 1. So, if I am giving a 0, whatever be the value over here previously, now it will go to 0. So, now this is the module D module where whatever be the output already present will not bother, only the D whatever be the value I am giving it over there is stored over there, and if I wanted to read it I will take only that. This is actually an D flip flop, which is the primary element which will be used for storing a single bit. So, by making a combination of all these D flip flaps, I will be in a position to store, I will be storing a word or I mean what will be the data. So, now I will be looking at what are the different units of data as well as the memory size are there. So, bit is the binary value, as we know it is 0 or 1, byte is a I mean one of the unit I will be using it where it represents about 8 bits, nibble is 1 unit which represents 4 bits, a word I can have it 16 bit or 32 bit or 84 I mean 64 bit. So, whatever be the size I can have it with your word. So, memory size. So, this tells you that I can store a single data with all these values. When I am looking at memory size, I will be in a position to have 2 power 10 or 2 power 20 or 2 power 30 or 2 power 40, which tells you about kilobytes, megabytes, gigabytes and terabytes. So, this is the way I will be having my memory. So, now we will see that quickly, we will see that the computer how you will be having it, where all these already we have gone through the digital circuit, we will gone through the memory. Now, I wanted to have a CPU which is nothing but a processing unit. CPU is nothing but your processor. We will be discussing in the further sections, and IO devices are connected, and RAM memory as well as read only memory, random access memory, read only memory, IO devices and your CPU is connected together to make a system. So, when you are connecting all those things, this has been done through the different data cables, which is otherwise called address bus, data bus and control bus. So, now you just see that this is the block diagram of a CPU, I mean of a computer system, where we will be having a CPU which is connected to read only memory, random access memory, printer, your monitor, your keyboard and disk through all these buses. So, this is address bus to address whichever unit, and this is the data bus through which all your data is communicated, and this is the control bus which will be giving information, I mean which will be the CPU controls all these units perform a task. So, with this I will be giving you a information about the computer system. Maybe I will be in this lecture I have gone through the different definitions of the system as well as I have explained what is an embedded system, and we have gone through the fundamentals of computing, and we discussed slightly about digital processing, and the different number system was discussed. The different logic gates which is used for digital processing is also discussed. So, digital circuits which is nothing but made it using a logical gate. So, I can call that also as a logic circuits for processing the number bits will also be discussed, and introduction to the system architecture is also covered in this lecture. So, these things if you wanted to refer any books you can refer. Some of the embedded system fundamentals has been taken from 8051 microcontroller and embedded system using assembly and C Muhammad Ali Masdi book. So, the other things you can cover it from whatever be the informations which I have covered in this lecture can be taken from any books which dealt about fundamentals of computing as well as the digital systems as well as logical gates, binary number system processing. Thank you.